inside of JavaScript, we have three types of scopes. Okay. You have lexical scope. This is when we use let-in consts. We have function scope. Which we'll go into more details. This is sometimes also local scope. I'll just put it over here, local. And then we have global scope. Okay, these are three types of scopes inside of JavaScript. Okay, so we'll first start off with lexical scope. So we can define variables using lexical scope by using the keywords let-in consts. Okay. And variables declared with lexical scope only exist inside of the scope in which they are declared. Okay, so a scope is defined as a set of curly braces. So this might be a function. Okay. So if I try to print out x over here, this will give me an error because x is not defined. It is defined inside the scope of A. But over here, we have a set of curly braces. So that is what defines a scope when we refer to lexical scoping. If I run this, I'll get an error that says x is not defined. And it's not just functions, it's also conditional statements. Okay. Over here, I have a statement if true, which will always execute. X and Y get defined. Okay. But as soon as I exit this set of curly braces, this variable is no longer defined. Okay. It's also for loops and stuff. Okay, so over here I loop 3 times. Okay, but as soon as I'm outside of that loop, I can no longer access variables declared inside of it. Okay. Now there is a second property that is almost obvious, but it's not obvious inside of it. JavaScript is one of the languages where this is not 100% obvious, in that in order to have, for lexically scoped variables, you cannot use them until after you've declared them. Okay, so meaning that this is fine over here, this is fine, but I can't do the following. I can't say console.log x and then let x equals 3. Okay, and this again seems almost obvious. Okay, but if we go into the next keyword which we're going to look at, which is var, okay, and var is a weird keyword because it fits sometimes in function scope and sometimes in global scope, depending on where you use it. Okay, and what we're going to be using it right now is we're going to be using it in the global scope context. Okay, so if we change this to var x equals 3, then this is no longer going to give us an error message. Okay, so notice that over here we got an error message that says reference error, can't access lexical declaration of x before initialization. Okay, this gives us an error message. But if I use this with var instead, there's no error message. Instead, I get undefined. Okay. Now, if I don't have this line, okay, if I don't have var x equals 3, then I get an error message. Okay, so it's not it's this line is adding some defense against this error. Okay, so essentially what's happening is there's a bit of syntactic sugar that's happening under the hood, and that's for global variables declared with the keyword var, we have this property called hoisting. And what hoisting does is it essentially lifts the declaration. So it lifts the declaration up to the top during the pre-processing step. Okay, so essentially what this is equivalent to is the following. Okay, so it lifts this declaration, not the assignment. Be very careful with this. Only the declaration. Okay, lifts this declaration to the top of the code, and then I no longer get an error because this is declared. And then I can use console.log, print x. What is x? X has not been set yet, so it's undefined. And then I replace it with 3. Okay, so if I run this over here, and I ask it, what is x? X is 3. Okay, this is essentially what's happening. Okay, we get undefined printed out, okay, because it's in a undefined state. Okay, so with let and const you can't do this. You have to declare your variables, and you don't get this weird hoisting property. Okay, so that is how var is used with the global scope context. Okay. Now, var can also be used in a function scope context. So we need to see the difference between those two. If I declare a function, let's call this function A. And I declare a variable, x inside of it. Okay. This variable x, if it's inside of a function, it is function scoped. Okay, so when you use var inside of a function, that variable is scoped to the function, meaning that it cannot escape the function. So if I try to print out x over here, this will give me an error because this is not a global declaration. Because this variable is declared inside of a function, this is a function scoped variable. Okay, so if I try to access x from outside of here, I'm going to get an error. Okay, now there still is a hoisting property. Okay, there still is a hoisting property in that this declaration of x gets hoisted, but it only gets hoisted to the top of the function. Okay, right. So how did the lifting happen if the code needs to be read line by line? This is goes back to that definition that I had. Do I still have it here? Let me go back. There you go. Lifts the declaration up to the top during the pre-processing step. Okay, so there is a pre-processing step inside of our interpreter where it goes through the code every time it sees a var something, and that var is either globally scoped. Okay, so we'll assume that's globally scoped. If it's globally scoped, it moves that to the very top of our code, and if it's scoped to the function, it moves it to the top of the function. Okay, so JavaScript does have a pre-processing step that will handle this. Okay, so let's talk a little bit about function nesting. Okay, so inside of JavaScript, you can nest functions. You can have functions inside of functions. And how scope works for this is that the child function, okay, the one that's inside, the inner function, it can access all the variables outside of it. Okay, so it can access all the variables outside of it, but the outer function, in this case function A, cannot interact with the variables inside of it. Okay, so let's clean this up a little bit. Okay, so in this example, if I have a function A, and in fact, again, let's be very concrete about this. Okay, so let's say that we have function A and a function. And function A, what it does is it declares a variable x, declares a function B, and uh, B declares a variable y, and then prints out x. I call B, okay, and in fact, let's do a commaless. Okay, so this will print out both x and y, okay, and then I try to interact with y, okay, but I shouldn't have access to y because y is scoped to B, okay, and A does not have access to B scope. So in this case, this one should give me an error. Okay, this should give me an error, but this one should work fine because B has access to Y, and B also has access to everything outside of it. Okay, so we can see that it prints out 1, 2 over here for line 5. Okay, and then for line what is it, line 8? Line 8, I get, well, over here, line 8, I get an error. It says Y is not defined. So there is one additional way to declare a global. Okay, so you can declare a global another way. Okay, if you don't use any keyword, so no keyword. I'm just going to put no key. Okay, so if you use no keyword when you're declaring a variable, okay, so over here, I'm using x without declaring it. Okay, then automatically this variable becomes a global variable. Okay, and it means that I can access this variable anywhere. Okay, so even outside this function. So if I run this program, this will print out 3. Okay, so this sort of breaks all the rules that we've set up since 1.11 about how data hiding works. So you should really avoid doing this. Don't do this. Always declare your variables, and ideally you want to declare them with letter const. These are the sort of modern tools that we use. We want this lexical scope. Okay. Very rarely do you actually want to use var. More likely, the case that you'll see var is because the code itself is just really old and they don't want to change it. Okay, but if you're writing new modern JavaScript, you should probably use letter const wherever possible. Closures is one of the key topics of this course. Okay, mainly because this course is very focused on asynchronous programming, and essentially in JavaScript, in order to do asynchronous programming, you need closures. But there are other uses for closures, which we'll look at today. So the 3 key mains of closures are factory functions, which are functions that generate other functions, namespacing private functions, okay, and asynchronous programming. These are the sort of 3 main uses. Okay, and for today, we're going to be focusing on the first 2. And then the next 2 classes will be going through asynchronous programming. So the idea is these are lesser used, but they will help us give us a intuition of how closures work. Okay. So let me first define what a closure is. Okay. So the definition that I like the most is the one by Kyle Simpson, who is the author of your book. Okay. And he says that a closure is when a function remembers the variables around it even when that function is executed somewhere else, executed elsewhere. Okay, so we're gonna look at some code, and then we're gonna come back to this definition, okay, to sort of take it apart. Okay, so this first bit of code, okay, we have a function make counter, okay, and what this function does on the first line or line 2, it declares a variable counter, which we assign the value 0 to it. And then the interesting bit is line 3. Okay, line 3, we return something, but this is something that we probably haven't really seen before. We're returning a function, okay? And inside of other languages, it's not very common to be able to do this. Okay, normally you return back some variable, okay, some variable x or something. But inside of JavaScript, we've already previously said that variables inside of JavaScript are first class. Functions inside of JavaScript are first class, which means that we can assign them to variables. And if we can assign them to variables and we can return any variable, then it obviously should be allowed that we can return a function. Okay, so syntactically, this is fine. Okay, so what we have to think about is what does it mean to return a function? Okay, so let's look at line 8 over here. On line 8 over here, we are calling make counter. And make counter, again, we're returning back this function. So essentially what C is equal to is C is a function. C gets assigned to it a function. And the idea behind this is I'm going to use this function later in my code. Okay, I'm just creating this function, and I'm going to use it later. Okay, and it looks like on so later could be some much later in my code because this is just a very small snippet of code. I use it on lines 10, 11, and 12. Okay, so it's important to know that it doesn't call this function. Okay, it doesn't call this function. It just saves it to C. And then when I call C with the parentheses over here, this is when I'm actually making the function call. Okay, so it doesn't execute this function until I call C. So essentially what make counter does is it creates a function, it gives it to us, we save it to a variable C, and then on lines 10, 11, and 12, we use that function that we created. Okay. Now there's something strange over here that sort of go against what we just learned about scope. It's that we have this variable counter over here, okay? And essentially what, if I take this function definition and I just move it over here like this, okay? If I take this function definition, I just move it over here like this. This is sort of intuitively what's happening inside of our head, but there's a problem in that we have this counter variable, and the counter was defined inside of here. Okay, so counter was defined inside of here, so it should no longer be in scope. Okay, so this variable should no longer be in scope. We should not have access to it. Okay, but we're using it inside of this function c. Okay, when I call c with these parentheses, I'm calling it. So let's see if it works first, okay? Because I'm not even sure if this will work, but I need to prove to you that it works. Okay, so it prints out 1, 2, and 3. So we do see that there's this counter variable, and that counter variable is being preserved. I can increase it and keep track of what it currently is at. So this does print out 1, 2, and 3. Okay, and so the question now arises is how is it able to keep this variable? Where is it storing this variable? Okay, and how can I access it even though it's no longer in scope? And that essentially is what a closure is. Okay, let's go back to the definition. So the definition says that closure is when a function remembers the variables around it. Okay, so the function in this case is the function increments. So it's when this function increments, let's call it c or increments. Where's my pen? There you go. C or increment. In fact, let's just call it increment and not C, because there's only one instance. Okay, so it's when a function, the function in this case is increment, remembers the variables around it. What is the variables around it? In this example, it's counter. Okay, the function increment remembers the variable counter even when that function is executed somewhere else. So somewhere else, in this case, is referring to lines 10, 11, and 12. Okay, even though I'm outside of the scope, okay, even though I'm outside of the scope over here, I can still access counter. Okay, increment still has access to counter. Okay, so how does this work? This is what a closure is, but we need to know how does it work. And the answer to this is a bit, to get the answer to this, we have to go a bit into how JavaScript manages memory. Okay, so we're going to go a bit into, we're going to touch briefly on memory management, but because I am not an expert on this topic, I'm going to try to keep it as high level as possible. So inside of most languages, including JavaScript, Java, C++, etc., the memory is represented as a heap data structure. Okay, and a heap structure, okay, is a tree-like structure. Okay, that holds the variables. Okay, so we might have a reference to, let's see, we might have a reference to C over here, which we'll call increments. Okay, and then C has a reference because it uses it. It has a reference to counter. Okay, it has a reference to counter. And let's say that this is the root of our program. Okay, the root of our program has a reference to C. Okay, because let's say that this program goes on for another 100 lines or something. Okay, if this program is really long, then much later on in the code, I should still be able to call C. I need to be able to, okay? Because it's declared lexically after this line, after line 9. Essentially, I need to be able to at any point in time, be able to say C with a bunch of parentheses, even if it's like down here or something. And it still has to be in scope. Okay. So the root, okay, needs access to C. So essentially what we say is that C is reachable. Okay. C is reachable. And we have this notion of reachability of is it possible for me to, should it be possible for me to access this variable? Okay. And then in certain cases, it's not. If I have something like if true, okay, and I declare a variable D over here, okay, then outside I should not be able to access it, okay, and then over here, essentially, go ahead and garbage collect. Go ahead and garbage collect D, okay, because I no longer need this variable D, but I can't garbage collect C because at any point in time I can say I need C, but it's not valid for me to say something like D++, okay, because accessing D has been cut off as soon as I'm outside of this block. Okay. And because I need to be able to access C at any time, okay, C preserves my access to counter. Okay, because C needs access to counter. Okay, so as long as we have something, we have this ability to reach counter in some way, then that variable cannot be garbage collected. Whereas other things, okay, that don't have a link to the root of our program, okay, for instance, that variable D that I just declared, okay, these things can be garbage collected. These are candidates for garbage collection. Okay, but essentially our closure allows us to prevent this variable from being garbage collected. Okay, and that's why, okay, that's why we can still use counter even though we are outside of this make counter function. Okay, and there's a special phrase for this. Okay, and it's often used as the following: we have some function, okay, and then the term closes over is used, and then we have one or more variables. Okay, so in this example, it would be increments. The function increments closes over the variable counter. Okay, and the way to think about this is essentially to say that increments preserves counter. Okay, it prevents it from being garbage collected. Okay, it preserves the scope. Now it's important to note that you as the programmer at this point in time, you can no longer access counter. I can't say something like counter plus plus, or okay, I can't access it unless I change the code inside of here. Okay, this essentially has been hidden from us at this point. Okay, I can't even say something like c.counter or something. No, none of this will work for me to access that counter without going into this function and changing it directly. Okay, I can only use it, but I can't change the value of it, set it to be like 1,000 or something without calling C 1,000 times directly. So now let's increase the complexity a bit. What happens if we change this from C to C1, C2? Change all this to C1. Okay. And then we're going to add another block, and we're going to call it C2. Okay. So the question that I posed to this class is, what prints out? Is it going to be 1, 2, 3, 1, 2, or 1, 2, 3, 4, 5, 6? Okay. That is each of these counters independent? or are they the same counter? That is sort of another way to rephrase this question. Okay, so think about it for a second, and I will copy and paste this, and we'll see. Okay, so the answer is it is 1, 2, 3, 1, 2, 3. Okay, so essentially each call to make counter, okay, it declares its own counter. So this let statement will essentially say allocate some new memory for a variable counter. And that memory is tied to this increment function because it's closed underneath of it. And then when I call make counter for C2, again, I am allocating some new memory that is tied to this increment function. Okay. But these increment functions are not, each of them are not associated with the previous one. So when I return a function increment over here, I'm creating a new function. So it's not a reference to the previous one that I had. So this is sort of the key, that this is not a reference. This is a brand new function that needs its own memory space. And it will have its own reference to its own instance of counter. All right, so C1 and C2 are its own unique functions. And we'll see this in the next example when we change the behavior of each of them. Okay, so meaning that C1 is independent of C2. If I keep on calling the function C1, this will continue on 4, 5, 6, regardless of what C2 currently is at. So this will be, right, so if I go back to here, I call C1, this should be 4, 5, 6, and then if I call C2 again, this will be 4 as well. Okay, each of these are independent of each other, even though they were made using the same sort of function over here. This will be sort of C1, and this will be C2. Okay. And so each of these will have their own instance of counter, which will be scoped to that function itself. Okay. So they're not related to each other at all. Okay, that's why we get 1, 2, 3 over here again. Okay, so let me give you some quick terminology before we move on to the next example. So you'll typically hear the following phrase a lot when you're talking about closures, and I just want to make sure that you are able to dissect it. So the phrase closing over is used a lot when we talk about closures. And so what this typically is defined as is it defines as a function closing over one or more variables. Okay, and with the case of the example that we had previously, it would be the function increment. Okay, so in fact I'll say function, that's fine, we'll just leave it, closes over variable counter. Okay, and what this essentially says is that the function increment over here is what is preserving the variable counter. This increment function is what causes counter to be preserved. Okay, so we'll look at the next example and we'll see something similar. Okay, so this second example uses a function called repeater. Okay, it defines a function called repeater. And repeater itself takes in two inputs, takes in a character and so a character is just a single character, and a times, which should be some number, specifically an integer. And again, we're returning back a function. Okay, so we're returning back a function, and this function, okay, it uses a method called pad start. So let's look at this method pad start. So pad start is a built-in method of the string class. Okay, so last time we we looked at this string class and we said that it has certain properties like length, and it has a bunch of methods, and all strings have this. So in fact, this includes the empty string. So the empty string has this property, okay, because of course this essentially becomes sugared into this, and then we have an object version of a string that has the function pad start to it, okay. Um, but this pad start function, okay, what does it do? It's a method that pads the current string with another string multiple times as necessary until the resulting string reaches the given length. The padding is applied from the start of the current string. Okay, so essentially if I say something like empty string, I want you to pad the character A 10 times over here, okay? Then what this is going to return back is a string with 10 A's, okay? Okay, so this returns back a function that essentially takes two variables, characters and times, okay? And that function, if we call that function, it's going to return back a string with that output, okay? So let's look over here. Over here, I define a variable A10, okay? A10 is set to be a repeater of A10, of A comma 10. So essentially, this becomes A, this becomes times, and I return back this function that looks like this. Oops. Return back a function that looks like the following. And where times is set to be 10, and character is set to be A. Okay, so this is what is sort of happening. Okay, it returns back a function, and if I call A10 at this point, okay, if we call A10 at this point, what is this going to return back? This is going to return back A 10 times. Okay. So let me run this to show you. Okay, so that defines the function, and now we're going to create A10. Okay, so it's important to know that A10 is a function. Okay, because this is a function that returns a function. So A10 is a function. Okay, so if I just type in A10 over here, it'll tell me that this is a function. Okay, but it doesn't run the function until I use the set of parentheses, which makes the function call. Okay, where did I mess up? This is A10 repeater. Did I have it backwards? Oh, I have it backwards. It should be character and number, not number and character. So let's try that again. Define the function. Define the generate A10, and then when I call A10, it should give me back a string of 10 A's. Okay. Now I'm going to define a second function, B20. Okay. And this is also going to use repeater to create a function. Okay. So this is where the term function factory comes from. This is a repeater is a factory that generates functions. I just give it the specifications that I want my function to behave like. Okay. In this case, I want a function that gives me back 20 B's when I print it out. Okay. Okay. So because of closure, okay, because of closure, if I call A10 over here, it remembers both the character that I want to print out, as well as the number of times it should be printed out. Okay. So if I type in B20, okay, it remembers both of these. So in essence, if we go back to our definition from previously, okay, then in this example, Okay. Repeat times closes over variables character and times. Okay, so we can close over multiple variables. And essentially what this is saying is repeat times preserves character and times. Okay, so the preservation of data doesn't, closures, they don't need to be just like some variable x over here. Okay, they can be the parameters as well. You can preserve the parameters values. Okay, so not only the instantiated variables over here, but as well as the parameters. Right, it's really good practice to use closures whenever possible inside of JavaScript. Okay, and so one of the questions would be, why would you want to do this, of course? Okay, and so, and one of the reasons you would want to do this is that you imagine that this, you would imagine that the pad start function, okay, you would imagine that the pad start function is actually extremely computationally expensive. Okay, and because it's computationally expensive, then you might not want to call it on the very moment that you actually need to call it. Okay, we have this notion of deferring the computation. So essentially, if we look at this example over here, okay, if we assume that pad start was extremely computationally expensive, on which line, line 11 or line 12, do we incur that cost? Okay. That is, if pad start was really expensive to do, okay, let's say that was really, really slow, then do I pay that cost on line 11 or do I pay it on line 12? Okay. And we can see that what does line 11 do? Well, line 11, all it does is it defines this function. Okay, it just defines this function. It doesn't run the function. Okay, it just defines this function, and then A10 runs it. The line after it runs it. Okay, so line 12 runs it. So this computationally expensive task is done later. We deferred it to when it actually needs to be called. Okay, so there's this notion of lazy versus eager that we need to talk about. Lazy versus eager evaluation. Okay. So in fact, this style of code over here that we've written, okay, repeater is written in a lazy evaluation style. Okay. And to sort of drill this, what's the difference between lazy and eager, I'm going to change the example slightly. Okay, to give you something slightly more concrete. Yeah, this one's fine. Let's hide this for now. Okay. So let's say that we had a function, okay, movie downloader. Okay. And what this function does is it returns back a function. Okay. Let's call this first frame. Okay, so let's call this function first frame. And what it does is you give it a movie name. Okay, so movie title. You give it a movie title. Okay, and what it's going to do is it's going to give you back a function. And when you run this function, okay, that function is going to download a movie. Okay, and this is a computationally expensive task. Okay, or a network expensive task. It's expensive in general. Okay, I have to spend a lot of resources to download that movie. Okay. Okay. So just like the previous, where does this expense occur? Where do I incur this expense? On line 9 or line 10? Okay. So I incur this expense on line 10 because on line 9, again, I'm just defining what this function does. I'm defining that my downloader is a function that when you call it, it downloads a movie, saves it to movie, and then it returns back the first frame of that movie. Okay, again, just we don't really have the code for this code because it's hypothetical. Okay, so this is like a bit of pseudocode. Okay, but it helps us understand that this is an expensive task. It had to download a whole movie, save it to a very movie, and then return it back. But it's not doing it over here. It's not running this function. All it's doing is it's defining what this function does. And then on the next line, I actually run that function. Okay. Now let's change up the code back to this. Okay. First frame and my movie. Okay. So let's say that we had a button on our web page. Let's consider a hypothetical web page that has a button on it. Okay. And then when that person clicks on that button, okay, then what happens is it downloads. Then it downloads that movie. Okay, but only when they click on that button. Okay. Now, let's say that in fact, don't even need this. Right. Let's say that button, it only gets clicked by 5% of our visitors. If only 5% of our visitors that are visiting the web page click on that button, then we would really want code that looks like this. Because how many times are we downloading that movie? If we have 100 visitors, we're downloading that movie only 5 times. Because the other 95 times, they didn't want to download the movie. Okay, only the people who specifically called this function, okay, they called this function, and how did they call this function? They clicked the button, okay? And for everyone else, we didn't run this function. Okay, so we can save computational resources if on average, okay, most users don't use that function. Okay, so this is lazy evaluation. It assumes that that most of your users won't use this functionality. And if it does, then at that point, I will use the expense. Okay. Now, the opposite of this is called eager evaluation. Okay. Eager evaluation is where you want to sort of do the work up front. Okay. Okay. So again, we have this movie downloader function. Okay. And the key difference between these first two pieces of code is all I did was I take this statement, okay, and I moved it outside of the return statement. Okay, that's the only sort of major change that I made over here. Okay, I moved this download movie statement outside of the return statement. Okay. And then this becomes eager. Okay. So the question now is, where is the expensive task being done? Is it on line 8? In fact, let's just call it directly. Is it on line 8 or line 9 in this scenario? Okay. Where do I, at what point in time do I make the expensive call to download movie? Okay. So let's trace the code. So over here, I define the function, and then I call line 8. What does line 8 do? It says movie downloader of movie title. Okay, so that goes inside here. And then the very first thing I do is I call the function download movie. Okay, so this is really expensive. So I'm doing it right away. Okay, so you can see that on line 8 is where I'm putting the expense. I'm front loading the costs. Okay, I'm putting the cost up front. And then what I return back is I return back a function that now when the person calls this function, okay, then I'm just going to take that movie I downloaded, and I'm just going to give them the first frame. Okay, so where's the benefit to this? Okay, why would I want to do something eager? Now the drawback is obvious. If we have a button over here and they have to click on it, if they never click on that button, then I just download this movie for nothing. Okay, there's no reason for me to download this movie because they never click that button. Okay, but let's say that they click on that button. Let's say that they click on that button 10 times. Okay, then in this case, this is really efficient because I'm not downloading the movie 10 times. Okay, remember what the code previous would look like. It looked like this. Okay, meaning that they click that button 10 times, then every time they click that button, I download the movie again just to get back to first frame. Okay, whereas with over here, okay, if they click that button over and over again, it's, well, I saved that movie already. Okay, I saved it to a variable movie. I'm just going to take that very first frame of that movie and I'm just going to give it back to you. So this is the expensive task is downloading the movie. It's not pulling out the first frame of that movie. Okay. So I should go into a bit of notation of what I'm doing over here with this syntax. Okay. There's sort of two ways to do this. So again, this is some hypothetical button, but we can either assign the function directly to it. Okay, that's one way to do it. Or I can use this arrow notation where I say that I'm creating a function that calls my downloader. You do not want to do this. This is the one thing that you should not do, because what this does is it calls my downloader. Okay, it calls this function. Okay, and let's say that pretend that the return value over here, movie sub 0, evaluates to a string. Okay, pretend it evaluates to the string first frame. Then essentially I'm assigning a string to this variable. Okay, and instead what I want to do is I want to assign a function to it. Okay, so this one is okay. Like this, if you do it like this, you're assigning the function definition to here. But this one is better because in this case, you're creating a new function that calls my downloader. And if you need to supply a data, then you can do that. You can't supply a data in the first case because as soon as you supply data, it does the actual function call. This doesn't do the function call. You're defining a new function. Let's see. Okay. So in fact, let's keep both of these up. Let's undo. Okay. So again, the key difference is just that we move this let statement uh, outside. We move this let statement outside of the. We move this download movies function outside of the return statements. Okay, so that we do the work up front. And what happens is that the closure preserves this variable so that we can access it later. Okay, so that's one way in which we can use closures. Okay, and so both of these have some pros and cons. You really have to consider what application that you're building to choose one of these two. Okay, do you think most of your users will need to access a particular resource? If the answer is yes, then you might want to do eager evaluation. You might want to front load all that work and then sort of cache the results, save the results, use it later. If most of your users will not need that resource, then maybe you'll do lazy evaluation. You'll compute the values on the fly when they request it. Okay, so one is not better than the other. Okay, but there is a better solution. There is a solution that has both properties. So it has the properties of lazy evaluation in that we only download the movie when we want, when the user requests it. Okay, we only download the movie when that function gets called, but we don't re-download the movie on every subsequent call. Okay, so the code for it looks like this. We declare the variable movie over here. Okay, and then what we do is we check to see if movie is undefined. And if movie is undefined, then we make our expensive call to download movie. And no matter what, we return back the first frame. Okay, so this is the ideal solution. Okay, in that we declare a variable movie. Okay, this is going to be first frame is going to preserve the movie. It's going to close over it. Okay, this variable. So we preserve this variable. So when we call it the first time, okay, let's say the person clicks on a movie to download a movie, then we are going to download a movie. In fact, this movie name should be up here somewhere. Okay, we're going to download that movie, and then we're going to save it to our variable movie. If we call it, if the person clicks on it a bunch of times, every subsequent click, we are no longer downloading the movie. Okay, because movie is now defined. It's set to be whatever we downloaded the value was. And so we skip this step and we return the frame of the movie. Okay, so if we call this multiple times, we no longer have that drawback of lazy evaluation. Okay, and so this has a special name. This is a memoization. And the only drawback to memoization is there is a memory. The drawback is higher memory usage. And so the idea is if I'm calling movie downloader a bunch of times, then after I call A, I have to keep this movie in my memory, okay, in case later on I call it again, okay? But if I only call it once, I still have to keep this movie in memory, and then I call movie B, I have to keep movie B in memory as well. If I call this, I have to keep movie C in memory, okay? And this is different with the lazy evaluation. With the lazy evaluation, as soon as I finish downloading that movie, that first movie, then it doesn't have any, the only variable that's declared over here is this one, okay? And that variable doesn't get stored. It gets garbage collected. So that movie is gone. Okay, so I don't need to keep that movie in memory. So there is a slight drawback with the memoized example, and that's why the name is memoization. You remember stuff that you did previously, okay? But that remembering has a higher memory consumption. When we do closures, it's important to keep in mind that these are not snapshots of the current value. A closure is a preservation of the linkage of variables. So over here we have an example. We have a function parent, and we have two variables. Okay, well, we have a variable foo, okay, and foo is set to be the string a. And then afterwards, we use foo, we declare a function use foo, and use foo will just print out the contents of foo. Okay, and we can see that this has that sort of structure where we have a function that sort of preserves the that creates a closure. Okay, that I'm going to try to I might use foo later on, and it's referencing foo over here. So essentially, use foo closes over foo. Okay, but then after declaring this function, I change foo. I change foo to b. Okay, if I then call use foo at this point, it will reference the new value. Okay, so it references the new value. Okay, so if I call this parent function, uh, it will print out b. Okay, so it uses the reference. It's not this sort of snapshot of the data. Right, the next example is namespacing namespacing private functions. This has a bunch of names. Sometimes it's called revealing module pattern. Sometimes it's called class-free object-oriented programming. There's a bunch of names for it. Okay, so the function dog takes in a variable n, and in that case, n is a string. Okay, and it assigns it to a variable name. Okay, and then it declares a variable age and assigns it to be 0. And it declares a variable inventory. It sets it to be the empty array. Okay. Inside of this function dog, it has 4 functions: bark, birthday, pickup, and display information. Okay. And each of these functions, they use these variables. Okay, they use these variables. So in essence, we can see this closure already. We can see that the function bark, it closes over the name variable. In essence, it will preserve this name variable when I go out of scope. The function birthday over here, it uses age and name, so it will preserve these 2 variables, name and age. You can have multiple functions preserving overlapping variables. And then we have the function pickup, which preserves the inventory variable because it needs it in order to do inventory.push. So these 3 variables over here are preserved by these 3 functions. Okay, so let's run this code first, and then we'll come back and discuss it a little bit more. Okay, so I'm going to load up this code, and then I'm going to create a dog. I'll call it let my dog1 equals dog of we'll call it Sparky. Okay, let my dog1 equals dog and Sparky. Okay. So what is this my dog1? Well, if we look at the code over here, the code over here returns back an object. Okay, returns back an object, and this object inside of it, it's a bit of a weird syntax, but let me remove the syntactic sugar to help you a little bit. Okay, this is a bit of syntactic sugar that I've removed. Okay, this is an object, so we know that an object itself is the following. It is a comma-separated list of 0 or more property value pairs, and each of these property value pairs is composed of a key and a value. Okay, so the key is how we reference it. So over here, if I say my dog1.bark, I'm referencing this property, and the value is any variable. So in this case, I'm setting it to be the function bark. That is a variable. Okay, so we know that these are variables. Okay, bark, birthday, pickup. These are all variables. And if you have this syntax where the property name and the value are the same, then JavaScript allows you to sugar one of them away, and it will do the duplication for you. Okay, so essentially we're returning back an object that contains three functions. And if I say my dog one dot bark, okay, without the parentheses, it will tell me that this is a function. Okay, but I don't want to see that this is a function. I want to use the function. Okay, so that's easy. I can just add parentheses. Okay, remember inside of JavaScript, when you save something to a variable, okay, if you use the parentheses, that essentially is calling the function. If you don't have the parentheses, that's telling you, it's giving you back the function definition so that you could maybe assign it to somewhere or pass it to another function or something. So in this case, I'm using that function, okay, which calls this bark function. And this bark function, it preserves the name, okay? So normally I should not be able to say something like my dog one.name, okay? Because the only properties that I have access to are bark, birthday, and pickup. So if I say something like my dog one.birthday, that's fine, okay? And I can run it a couple of times, and I can see that it's keeping track of age because I know age initialized to 0, and then every time I call birthday, it increases it by 1 with this age plus plus statement over here. But there's no way for me to directly interact with that age. So I can't say something like, tell me the age. It says that I don't know what the age, it's undefined. Okay, well, can I set it? Can I say something like my dog one, the age is 100, and then I call birthday a couple times? No, it'll just ignore whatever I did, okay? Because this is the power. It gives us this data hiding properties, okay? So essentially we can treat this as a class, okay? This is how JavaScript did classes before ES6, okay? And this is still a very powerful technique. Essentially, these variables over here, name, age, and inventory, are privated. They are privated via closure. The closure preserves them, and we can't access them directly, okay? The only things we can access in this case are the methods that we return back. And this really strictly is methods. If you try to pass in the property names, it breaks all sorts of stuff. So if you actually do want to interact with the name, age, and inventory, you should set up getters and setters as specialized functions. Returning back the name, age, and inventory causes problems. Now over here, we did have 4 functions. We had this function display inventory. So can I call this function display inventory? And the answer is no. So this method is also privated. Okay. The only thing, if I do want to access this method, then I have to include it in the list of functions that I'm exporting out. Okay. But I do want to keep it private. I don't want the user to have access to this function. Okay. And instead, how do I use this function? Well, this function is preserved by the function pickup. So essentially, pickup, okay, so pickup closes over inventory as well as display information. So because, again, functions are first-class variables, we can have functions that close over other functions. Okay, so pickup, well, it closes over inventory. I use name over here. Right, it's just name and inventory, and as well as this display information function. So those are the 3 things it sort of closes over. And so if I say my dog one dot pickup, let's say a bone or something. Okay, let's say Sparky has picked a bone. They have a bone in their inventory. And then I also give them a stick or something. Then we can see that this inventory array, it works just fine. Okay. And of course, because if we create a new dog, okay, we create a new dog, then they also have methods and the actual underlying data is independent of the other dogs. Okay. So we can sort of use this namespacing private functions to create objects in a class-like structure. Okay, so that's another way that we can use closures